Welcome to our Corona Beardy sketch. We will, of course, cover the newest member of this family, the virus that causes COVID 19, as well as its cousins, the causative agents of SARS and MERS. We'll also throw in a few mentions about the four less pathogenic and less well known human coronaviruses. Welcome to the Corona Kingdom, a land of everlasting summer, verdant forests, and beautiful sunrises. Nah, just kidding. It's a socially distanced serfdom. But let's take a tour of the castle anyway. Masks on! Corona is Latin for crown, and that's because of the crown-like spikes on its surface. These spikes, also known as peplomers, are pretty important, so we'll be coming back to those peppy peepers in a bit. First, some basic specs. Coronaviruses are single-stranded, positive-sense RNA viruses. We've set the scene in warm orangey hues, which should tip you off that we're talking about an RNA virus. And rising above the horizon, you'll see a positive-sense sun. The positive-sense part means that the genome can also serve as messenger RNA. We'll come back to the implications of this in our discussion of the life cycle. There are 7 coronaviruses known to infect humans, but prior to the beginning of the 21st century, there were only 4, all low pathogenicity viruses that cause the common cold. That's why this commenter out here with the case of the sniffles looks pretty unthreatening.
Unthreatening? Just wait till I drop the Magna Carta on this Middle Ages milksop. Forsooth.
These viruses are considered endemic in humans. And see, no animals in sight. These viruses continue to circulate worldwide, but they're not even famous enough to get pronounceable names. The 3 newer coronaviruses are, of course, quite a different story. They're all zoonotic viruses that have crossed the species barrier to cause deadly respiratory illness on pandemic levels. All 3 viruses likely originate in bats, aka the primary host or natural reservoir. The intermediate host varies. Palm civets in the case of the original SARS-CoV and dromedary camels in the case of MERS-CoV. SARS-CoV-2, the COVID-19 virus, may have had an intermediate host or may have been directly transmitted from bats. We'll depict the 3 highly pathogenic coronaviruses on this banner above, starting with these SARS stars. That's because this whole mess started with SARS-CoV, which, by the way, stands for Severe Acute Respiratory Syndrome Coronavirus. The OG SARS-CoV emerged in 2002 and causes, you guessed it, SARS. Next came MERS-CoV, or Middle East Respiratory Syndrome Coronavirus, in 2012, which causes, MERS. Not a very creative move by the International Disease Naming Committee, but whatevs. Anyway, astrology teaches us that you're most likely to contract this disease while under the baleful influence of the red planet Mars. And, of course, the newest addition to the family is SARS-CoV-2, the virus that causes coronavirus disease 19, better known as COVID-19. The virus was named SARS-CoV-2 because it's genetically similar to the original SARS virus. We've added these 2 shooting stars in the shape of a 19 to remind you of SARS-CoV-2 and COVID-19. Now that you're familiar with the corona royal family, let's move on to structure. Most coronaviruses have 4 structural proteins that form the virion. What's a virion, you ask? It's the fully formed virus particle typically seen outside the host cell and capable of infecting new cells. At the core, you've got the RNA genome bound to multiple subunits of nucleocapsid, or N protein. Together, they form a nucleocapsid with the helical shape. We've sketched an orange helical tower with an N door to remind you of this, and we even made the hills and trees spirally so you extra won't forget that these little squirmy devils have a helical nucleocapsid. The nucleocapsid is surrounded by a viral envelope, just like this king is enveloped by a luxurious robe. So yes, coronaviruses are enveloped, meaning they have a lipid bilayer studded with proteins. The coronavirus envelope typically contains 3 different proteins, all of which are in the possession of the king. His crown is embellished with the letters ME, like a real king, like a king with self-respect, and possibly narcissistic personality disorder. And his scepter has a beautiful S on it, for scepter, I guess. Take a look at the sugary shapes on the surface of the king's scepter. The protruding portion of the S protein is heavily glycosylated. It's these large, widely spaced glycosylated knobs, or spikes or peplomers, that give coronaviruses their crown-like appearance. But these spikes are far from just decorative. they're responsible for entry into host cells, including receptor binding and membrane fusion, which we'll talk about in just a sec. So far, we've been talking about coronaviruses in general, but let's shift our focus to take a look at the life cycle of SARS-CoV-2 specifically. Pay attention, future Nobel laureates. Any of the stages of the life cycle are potential therapeutic targets. The receptor for SARS-CoV-2 is angiotensin-converting enzyme 2, or ACE2, hence the ACE2 hand held by the king's opponent. ACE2 is expressed on a number of different cell types, most notably type 2 alveolar cells in the lungs, and no suit looks more like those bubbly alveoli than clubs, hence the 2 of clubs. The original SARS-CoV uses the same receptor. In contrast, MERS-CoV uses a different receptor, dipeptidyl peptidase 4, or DPP4. Let's take a look at how SARS-CoV-2 gains entry into the host cell. It all starts with the spike protein, which is the part of the coronavirus that actually binds ACE2 on the target cell. After binding, the spike protein undergoes a conformational change, allowing it to facilitate viral entry through the fusion of viral and host membranes. Once a virus has gained entry into a host cell, the series of events appears to be very similar across the different coronaviruses. The virus uncoats as it enters the cytoplasm. Of note, the virus will stay here in the cytoplasm for its entire replication cycle. This is true for most RNA viruses. There's no need for DNA intermediates and no need to enter the nucleus. You can think of this table as the cytoplasm of the host cell. We'll be depicting the rest of the SARS-CoV-2 virus life cycle here with gifts set out for the king by the 3 wise women of the kingdom. Once the virus has entered the cell, the first order of business is protein production. The immediate production of proteins is possible because of the positive sense RNA genome, which we'll represent with orange sun necklaces. Since it's structured like messenger RNA, it can be directly translated by host cell ribosomes. That's exactly what happens here. A key gene, called the replicase gene, is translated into 2 long polyproteins, represented by 2 giant proteinaceous mutton chops. And take a look at these protein-cutting meat cleavers that came with the mutton chops, a recurring symbol for proteases. After translation, the viral proteases actually cleave themselves from the long polypeptide chain, which is called autoproteolysis. Freedom! Once free, these proteases process the remaining polypeptide chain, releasing a whole bunch more proteins. Many of these proteins perform crucial roles in replication and transcription, and associate with one another to form the aptly named replication transcription complex. The key member of this complex is the so-called RNA-dependent RNA polymerase, or RDRP, which the virus uses to make more copies of the genome from its own RNA. The RDRP uses the positive sense genome to make a negative sense copy, which is then used as a template for more positive sense RNA. No DNA intermediate needed. Just like the virus, this wise woman is using positive sense necklaces to make negative sense molds, which she can then use to make more positive sense necklaces. The full positive sense genomic RNA is also used to produce shorter RNA segments that ultimately lead to synthesis of viral proteins, which is how the S, M, E, and N proteins we talked about at the beginning ultimately get made. These newly synthesized structural proteins are the building blocks for the next generation of viruses. Let's take a closer look at the assembly process. The S, M, and E proteins, just like your typical membrane protein, are translated at the endoplasmic reticulum where they're folded and packaged into vesicles for transport. From there, they're shipped off to the Golgi, represented by our recurring Golgi goldfish. Meanwhile, in the cytoplasm, the N proteins associate with freshly transcribed positive sense genomic RNA, forming the helical nucleocapsid. This is where coronaviruses get weird. The nucleocapsid of your averaged envelope virus usually waits for the membrane proteins to make it all the way to the cell membrane before joining up and budding from the cell surface. The coronavirus is a little different, because it buds from the Golgi instead of the cell membrane. It still has to actually get out of the cell to do its dastardly deeds, but technically it's a fully functional virus once it's budded from the Golgi. The finished virions are then transported through a series of membranous vesicles to the cell membrane where they're released via exocytosis. Bloop! Alright, now that you're familiar with the coronavirus life cycle, let's move on to transmission and clinical manifestations. Coronavirus may be transmitted by aerosols or droplets, though the jury is still out on which is the most important method of transmission. So for now, just remember this sickly dude coughing a whole bunch of gross droplets all over this poor Knight 95. who's fortunately wearing a specialized piece of armor to block aerosol transmission. As we've mentioned, the 4 less pathogenic coronaviruses cause mild upper respiratory illness, basically the common cold, hence this commoner with a tissue.
Commoner? You take that back, you boiled newt! Forsooth.
So, yes, the case of the sniffles you had a while back, that could have been a coronavirus, or any of the other viruses that cause the common cold. The more pathogenic coronaviruses can all cause severe, potentially deadly pneumonia, which is why our friend with the dirty lung spots is standing next to another Stars and Mars tapestry. Let's talk a little bit more about COVID-19 specifically. This disease has an impressive range of severity. Some people are even asymptomatic. That's why the king in this painting is happy and asymptomatic. Among people with symptoms, the majority are relatively mild, including fever, cough, and in some cases, upper respiratory symptoms. Though some patients report GI symptoms and even changes in their sense of taste, ageusia, and smell, anosmia. A smaller percentage develop severe, life-threatening pneumonia, hence the dirty lung spots on this chest plate. In addition to fever and cough, these patients also tend to have dyspnea. Severe cases may be complicated by ARDS, and consequently a need for mechanical ventilation. The development of ARDS may be related to cytokine storm, in which the immune system essentially overreacts to the viral infection by releasing excessive cytokines, which can damage tissues. And the bad news doesn't stop there. That immune overdrive can cause all kinds of other problems, like MI, PE, or stroke. The diagnosis of COVID-19 is typically made by detecting the genetic material of SARS-CoV-2 with a nucleic acid test, or NAT, depicted by our recurring swarm of gnats. The most commonly used NAT is RT-PCR, also known as reverse transcription polymerase chain reaction. This test is usually performed on a sample from the respiratory tract, typically a nasopharyngeal or nasal swab. Yeah, this spear is ineffective for spearing, but it's great for sample collection. These same types of swabs can also be used for a second type of diagnostic test, antigen testing. This involves detecting a part of the virus itself, for example, the nucleocapsid protein. Another important type of test is serology, which specifically looks for the presence of antibodies in the serum. So we've included another guard with a quiver of antibody arrows. Most of these serologic tests measure IgG, but some measure IgM. Since antibodies take time to develop, the main role of these tests is not to diagnose active infection. Instead, they're used to determine if a person has a history of infection, though we don't yet know how long these antibodies stick around. Currently, management of COVID-19 is largely supportive. But of course, a number of therapeutic agents are being tested in clinical trials around the world, and a number of vaccines are in development. Hopefully, we'll have an update to this section of the video soon, and we'll talk about how SARS-CoV-2 is preventable with a common vaccine.
Common? Again? We talked about this, you pusillanimous poltroon. Forsooth.